Hello, Anthony. That's all right. Hi, Chris. How are you? Okay, so we are going to do Unit 7 today. We'll start in a couple minutes. If you can please check out Canvas. Let me make sure it's able to view in the page there for the notes. Okay, so we'll start in a minute. If you can please check out your assignment and your notes. Okay, so welcome back. This is week 7. We're almost halfway through. And so in this week, we are going to work on searching and sorting. And our lab is going to be based on this. So for this session, we are going to talk about different type of search and sort algorithm. And we are going to look into how that can be used in programming, like in C++ for our lab. So if you do check out your assignment, that's in Canvas for Unit 7. And so now I'm going to go over the notes. So it starts with talking about algorithm, and that's just a process or a set of rules that can be followed in calculations or to solve a problem. And we are going to focus on how the system is going to search for a key value or for a certain item, and how it's going to be able to sort. And we are mainly going to focus on ascending sort, going from low to high or A through Z. Okay. So now the goal for search is to really find an object in a collection. So you will have a container. For example, we can have an array. And in our array, we would initialize the value in the indices. Then it's going to go through and it's going to try to identify that object if it exists in that container. And there are different types of search algorithm that's implemented. So your object that you're searching for would have some kind of value. If we're looking for a certain number in our container that contain integers, we can have it search for that specific value, or it can also search for character, strings, and so on. And this is important because you would see the application that we use every day would require this. So when it's sorting the content of that container is when it's rearranging the objects from low to high if we're going to go ascending, and if we go descending, it's going to go from high to low. Now the object can be sorted by the key value, so we would see that we can sort it a certain way. We can tell it to sort, and you would know that there are STL or library that would already implement certain type of sort algorithm and search algorithm. But we are going to look into the details on how some of these differ. Okay. So to start, we would have an unordered linear search, meaning that we would have a container and the values are not pre-sorted. They are out of order, and we are going to go through that container and look for a certain value. So for the object to really, so here it says that in order to determine if the object exists in the collection, it would then need to go through the entire collection in some cases. So let's say that I have this container, for example, I have 34, 16, 12, 11, 54, 10, 65, and 37. And these numbers are not sorted. They're not arranged from low to high in any way. And if I'm looking for a value, such as number 11, it would then need to go through and check every single index to see if that value exists. So when it gets to the index 3 or the fourth element, it would say that it found 11. But what if I look for a value that doesn't exist in that container? Let's say I'm looking for the value 100. It would then need to go through the entire array and tell me that that value cannot be found. So in an unordered linear search, in the worst case scenario, we would know that there, in the case that that object doesn't exist, it has to iterate through the entire container to really provide the result that that particular value doesn't exist. So in our example, number 11 is on the fourth element. So it would then need to examine the first 4 elements in order to find the number 11. And when it found the 11, it's going to stop. Okay. And that's the whole point, is whatever the key value that you're seeking, it's going to stop when it found it. But if it doesn't find that value, it has to go through the entire container. Okay. So when we're analyzing this type of performance, we would consider the count for the examination or examination counts, as then it would be depending on the number of elements that exist in that container. So if I have an array that has 100 elements, and if I'm looking for a certain value that doesn't exist in that array, it has to go through the 100 elements in order to tell me that that object doesn't exist. Now, for the unordered linear search, we start with the non-sorted container. On the next one, we would have a pre-sorted set of values. Okay. So for the ordered linear search, it's still going to be going through, and each of the element, it's going to try to compare. And once it found that element, it's going to quit. But your array would then become pre-sorted, so that way it would be easier to really analyze. Okay. So if the array is then sorted, one need not to necessarily search through the entire list to really find a particular object, whether it exists or not. Okay, so we would know that the first half that will be left, okay, would be from small to large values. So if I'm looking for 34, right, I would know that anything prior to 34 would be lower, okay, because it's going to arrange from low to high. So from left to right, you would know that the smallest value is going to be the left and the largest value is going to be the right. So then the search is then can be terminated early if and when it is determined if a number is sought. And if it's yet not to be found, is less than an element that's currently examined. So if I'm looking for 34, it's still gonna look for the first half, right? These elements, it's gonna look for the first element, second, third, fourth, and then when it gets to the fifth element, it's gonna stop. But we would know that anything prior to that fifth element would be smaller than it because it is sorted, okay? So is there a better way to really approach it? Sure, you can. You can look at how you would be able to compare, right? Based using, greater than, less than operator and so on. So we'll talk about other type of search mechanism there. So in an ordered linear search, different than an unordered linear search in that we would have to pre-sort our values in the container. So for the first couple questions, it's pretty easy. It asks you to describe the similarities and the differences between ordered or unordered linear search and ordered linear search. Let me zoom in on this a little bit so it's a little slightly larger for you. Okay. So then we would know that an unordered linear search, it needs to determine if that object exists in the collection by searching through the entire collection. Whereas the ordered linear search, given the array that is sorted, that's the main difference. One need not to necessarily search through the entire list to find a particular object to determine whether it exists or not. Okay. While it scanned the array from left to right, from smallest to largest value, the search can now terminate it if and when it is determined if a number is sought. So when it found that key value, it's going to stop. And as yet not found, it is less than the element currently examined. Okay, so depending on the sequence of values that we place into the array, of course, but then it's going to be, if it's not found there, right? So if you look back in the notes, if 34 is not found there, when it goes to the next index, it will be higher than it. So then you would see that it would be one less, as in it's going to reach up to the one prior to that value, and it's going to know whether it exists or not. Okay, so there's some slight difference between the first and the second, which is the unordered and the ordered search. Any question with linear search? So when we implement this in programming, we would need to think about how we can incorporate loops, right? We would then need to also apply the conditions. And when you're working with an ordered linear search, you got to make sure that no matter what type of value that you have in your container, you have to make sure that you issue a function sort. So you have to execute sort. So that way it would arrange your value from low to high. Then you would then need to iterate or loop through it and examine the index. So in the case where if you have 1,000 or 10,000 elements, right? When you're looking at an unordered linear search, it has to go through the entire array to really check to see if that element value exists. Whereas ordered linear search, in the worst case scenario, it's going to be less than the element that it currently examined if it cannot find that value. So if I'm looking for a value 101, right, it's going to be all the prior elements to 101 that it needs to examine. Any question on this? So for quiz, exam for this course, make sure that you know the difference between the two, okay? How it's seeking the key value and the primary difference there. Okay. Then we have another type of search. And in this particular textbook, and some textbook, they use chunk search. Okay. And so chunk search is a way that we can take the container and chunk it up into subsets. Okay. So you would have a collection, and then it would divide up that collection into chunks, where it would then group the elements up, and then it would examine based on each group. So how does it really chunk it? It would take the number of elements, which is your n or your I in this case, and it's going to take a square root of that. Okay. So your C size or your chunks is going to be the square root of the number of elements or the input. Then your search key, the value that you're looking for, is going to be compared to the maximum value of the first chunk to see if it exists in the first chunk. And if it doesn't, it's going to go to the second chunk and then the third chunk and so on. So if we're looking for the number 34, it's going to take that 34 and it's going to compare that to the highest value in the first chunk, which is 12. And sorry. And as it is bigger than 12, it's going to move into the second chunk right away and not waste time looking at the first chunk anymore. So when it goes into the second chunk, it's still gonna examine, right, linear wise inside that second chunk. So it knows that it's need to be in the second chunk. So when it checks 16, smaller, and then when it gets to the next element, 34, it found it and it's gonna stop. So chunk search is faster than linear search in that we can break up, right, our container into subsets or chunk, and then examine the highest value in each chunk. And so it can narrow down on which chunk it will be able to find your key. So here it provides you with the details on how 34 is compared to 12, that's greater. So it moves into the second chunk. And it's going to go to 37 because that's the maximum value of my second chunk. So that is, it's less than that. So it concludes that it's going to be in the second chunk. It's going to find it. Okay. Now, if we are asking it to find number 33, and if it's not found, it's still going to look at, right, each of the chunks. So greater than 12, it's going to try to find it here. And if it's not able to find it here, it's going to tell you that it's not found because it cannot move higher than 37. So implementing this algorithm, you must also make sure that it's pre-sorted. Okay. So then we would then chunk it up. And it doesn't have to be completely equal in the number of elements, but it will be close enough, right? We saw in the last example, we would have one chunk of 3, another chunk of 3, and then our last 2 elements is going to be in the third chunk. Any question? Okay, so then when we go over to our assignment, we would compare chunk search to linear search. So in chunk search, the collection is divided into chunk or subsets, which is known as C. And RC is going to be equal to the square root of input, or N, or I is just the number of elements, right? So the search key is then compared to the maximum value of the first chunk. If the search key is greater than the maximum of the first chunk, the second chunk will be evaluated, and so on. So after it breaks up into chunks, it's still gonna linearly looking through all the chunks. However, instead of looking at every single element, it's gonna look at the maximum value in each chunk to narrow down which chunk contains the key. In the linear search, each element is compared in an unordered linear search. Simply iterates through the array, examine its element one by one. In the ordered linear search, the elements are compared and the search is terminated as soon as the key is found. So you do see that the performance is boosted when we chunk up our container compared to linear, where it has to examine, in the worst case scenario for the unordered, every element in that container. Okay. Any
So,
questions?
Professor, does for the chunks, do we as the programmers establish the size of the chunk, or is that something that's automatically determined?
So in this particular approach, it is a square root of your input. And we will see this in the lab, right? So you have to program that in, right? You would say C is equal to, right? So you would say C equal and then square root of N, where N is going to be the size of your array.
Okay, got it.
Very easy.
Yeah.
Super easy. So in the algorithm, you have to tell the computer what kind of rules is it applying, right? So the rule that we are telling it in the chunk search would be that our chunk is going to be this size, square root of N, and N is going to be the size of your array. So that goes into the declaration of your variable, right? C is a variable and how it's going to use that variable to be able to focus on. So we can break up now that our container into sub-container or sub-arrays and then evaluate it there. Okay. Question. And you don't have to write all of this stuff verbatim. Just keep in mind that I do. I'm fine with you summarizing it, but I put it so that way it's clear in the case if you need to refer to it. And then when I explain it, it's just clear for you. So however you want to maintain your assignments and notes, that's fine. Okay, so the whole point in this is to help you understand and remember. So that's why we're doing these assignments together. Okay, so we have examined the linear search in unordered and ordered, and we talked about the chunk. Let's go a little deeper into the chunks. Okay. So if you're looking at these algorithm and you want to compare them, right? Then you need to think about what would be the performance, which is measured in time complexity. We already talked about this in one of our labs. Okay. That is the amount of time that's going to require to run the algorithm. So now commonly we would always refer to worst case time. Rarely that you would see that things are measured in average time. The worst case time is in the worst case scenario, how is your application performing, right? With the, with very old hardware, with, slow connection, with minimal resources, how is the application performing? So we want to measure it in the worst case scenario. Now, less common, you would see that some cases they would measure in an average case scenario, the average time that it takes on the inputs from the given size. And when you're dealing with search and sort, the dependency would always be the size of your input. So if I run an application, right, using the same algorithm for an array that has 10 elements compared to 10 million elements, of course, the 10 million is going to be slower, okay? Because now that you would have more input, especially when you're looking at linear to test. So then it has to go through 10 million elements in the worst case scenario. So we would use the big O notation. And in this, these are the 4 steps in how you would develop a solution to solve a problem using algorithm. Okay. So first, you would design an algorithm or a step-by-step procedure to solve that problem. And in this class, we addressed a lot of the things mathematically first, so that way you would take that concept and you would apply that to programming so you can see how you can solve it program-wise, right? Now, once you have the step-by-step procedure on how you would solve that problem, so I would start with like the mathematical, so, steps, and then bring that into the programming. Okay, so if I need to examine every single element and check against it, then I just implement a loop. And then I can nest in an if and an else, or an if condition. So that way, we can specifically look for certain things with a certain criteria. So once you have the step-by-step procedure, then you want to check for correctness. And we spent a lot of time last week doing this, right? I showed you how you can have something that's output as a program, but is it really accurate? Is it representing what we would see realistically in our everyday world? So then if it's correct, then you want to check for efficiency for the procedure. And remember that we always going to have, you have to compensate. If you're using more storage, okay, then you're going to gain time. If you're having more time, then you can reduce space. Space and time is always going to be, there's the inverse relationship there. Okay. So we want to check to see if a program is efficient. And that means that we have to look at time and space and how your procedure is used. So in the advanced programming class, we would then go back to the algorithm and how you can improve it. And sometimes we would think about how the machine is handling that instructions. So for example, in my Python class this week, we looked at how resources are used. So when you're running it line by line, when you pause it at a certain line, it frees up the resource for the later line and it would execute the other function or queue it. And you see this with processes in operating system as well. So, designing an algorithm is not just a one shot, right? You have to go back and you have to redesign it. So once you analyze it's correct and efficient, then you're going to implement the procedure in language, and then you test it. Okay. So if you have a higher number of input It's going to take longer. We set that. And the type of algorithm that you're using, right? That's going to really speak to how fast or how good of a performance is your application. So when you see these tech company that they're interviewing the candidates and they're giving the problem for the candidate to solve, what are they really looking for? These things, right? How correct is it? How efficient is your program? Okay. Now, programming language plays in this. Okay. C, fast. C++, also fast. But when you get to some other areas, while other programming languages are preferred for certain organization and overall easiness, right? Simplicity in the syntax, right? Not necessarily fast. So a lot of times when you're looking at something that's older, like BASIC compared to C++, BASIC, right, is slower than the compiled languages for C++. If you're looking at something like Python using pure Python interpreter, and I proved this in my class in the last couple of weeks, we actually run a time test on when it's compiled compared to when it's running through the interpreter. Definitely shave off some seconds for the same number of inputs. So compiled languages tend to be preferred for a lot of times for performance reason. And then also looking at the implementation, how clean and tight is your code, right? And is it going to be, that's going to really present how fast or slow or how poor the program would be. You still might have the same output as the other, right? So we wanted to make sure that it's good and clean and tight. Okay, so think about data structure, think about objects when you're using OOP. Okay, think about how you would approach that. And then if you're using modularity, right, like writing different module, how each of the module sees each other. And so when I say module, what do I mean? They're just different program files that are interconnected to work as a bigger program. Okay. So here it touches on a little bit on efficiency again, worst case scenario, and a good worst here. This is important to note. A good worst case running time will always be fast. Okay. On the other hand, an average case analysis aims to determine how fast the algorithm is on average for a typical input. So in that case, the worst case running time of an algorithm is quite slow, but in reality, the typical inputs the algorithm is much faster. Okay, so see the difference there. Okay, so there's some highlights about worst case analysis. And then, so bringing this back to T of N, okay? So in the linear search, since it's looking for the key by checking each index, your T of N is going to be, or your O of N is going to be N. Okay. In the chunk or in a lot of the C++ textbook, it's going to call that the jump search. Okay. Just the same, different way to call it. So we already know the mechanism of this. It's going to size down your array into different chunks. So when it's looking at the chunk, your O of N is going to be, or your T of N is going to be N divided by C plus C. Okay. So N is the number of input divided by the chunks size and then plus the chunk size or the number of chunks. Okay. So if you have lots of chunks in the worst case scenario, right? Compare that to the worst case scenario for linear. Jump search or chunk search is faster still. All right. So when we put this, how did they come up with a chunk is the square root of n, right? So if you have c is going to be equal to n divided by c, you move the c over to the other side algebraically, you would have c squared is going to be equal to n. So your c is going to be square root of n for jump search or chunk search. So if I have 100 elements, I just take a square root of 100. So my chunk size is 10 elements per chunk. Simple. How many chunks do I have? 10. Right? So we simply take the number of elements. We would then take the square root of that. That tells us the chunk size. And based on that, you take the number of input divided by chunks so you can actually see how many chunks you have. Okay. And so for your desired chunk, your chunk size is square root of n. We established that. Your T of n is going to be the number of input divided by your chunk size plus your chunks. So like we said, if we have 100 elements, we would do 100 divided by 10 elements each, right? Plus 10, and that's going to be your T of n. So if we expand this, okay, we would say that your T of n officially is 2 times square root of n. So if we have 1,000,000 elements in an ordered linear search, worst case scenario, if it doesn't find it, it has to go through every single element. In the chunk search, that requires 2,000 examination because we would take 1,000,000, we would take a square root of that, times it by 2, which gives you 2,000 examination, which is 500 times faster than the ordered linear search. Okay. Any question on this? Let's do the next few questions on our assignments. So for 3, what is the purpose of having a worst case analysis in algorithm analysis, right? Analyzing algorithm. So it aims to determine the slowest possible execution time for an algorithm. The worst case analysis is useful because it tells you no matter what, the running time of the algorithm cannot be slower than the bound derived. An algorithm with a good worst case running time is always fast. On the other hand, the average case analysis aims to determine how fast an algorithm is on average for a typical input. It may be the case that the worst case running time of the algorithm is quite slow, but in reality, for typical input, the algorithm is faster. Okay. So from here on out, when we try to measure this, any kind of application, we want to look at the worst case analysis. All right, let's look at time now. So for number 4, we would say when searching through 2,000 elements in a vector, assuming that the system takes 0.5 nanoseconds, that's not bad, right? To search through each element, how long would it take to search through the entire vector using linear search? So it would then, that's easy. You would take 0.5 nanosecond. For the linear search, it's the number of input. So there are 2,000 elements. So we would multiply that by 2,000, which gives us, right, 1,000 nanoseconds. And if you want to really convert it, this is the number of minutes. You can leave it in nanoseconds, that's fine. So for number 4, we already know that if we search linear, that's going to be the time, right? Number 5, it asks you if an application uses chunk search to find matches in 100 elements in an array. What is the chunk size in the worst case scenario? So your n value is 100. Then you need to find your c. So you would take a square root of n, which is square root of 100, and that's going to give you 10. So we would have 10 elements per chunk, and then we would have 10 chunks. And when it compares, it just goes to the maximum value for the first chunk, check that, then go to the next one, check the maximum value of the next chunk, and then so on. Okay, so 5 shows us how we can find the chunk size. And then we'll talk about binary next. Any question? Okay, so quiz and exam, make sure we know how to determine chunk size. Then on page 5 of your notes, it begins covering binary search. And this is what you see quite a bit, right? When you're looking for search algorithm, binary usually pops up because it's the preferred way. It's the fast way. So if we take an array and we cut it in half, that's going to be n divided by 2. And what if we half it again? So that would be n divided by 2 divided by 2. And then we half it again, and we keep going until we get down to one single element. So if you start with 100 element, you cut it in half, you have 2 halves, 50 and 50. Then you half it again, then you have 4 quarters, right? 25, 25, 25, 25. Then you take that 25 and then you half it again, right? So you have 12 and a 13, 12 and a 13, 12 and a 13, so on. And you keep going until you get down to the single element. And so as it does that, it's going to quickly find the key by looking at halves of the halves of the halves of the halves and so on. So when we take the expansion, when we divide it into half and we convert it, we really see that K is going to be, so in general, when you cut it in half, the K times yields the array of n divided by 2 to the power of K, because we keep subdividing it into halves and halves and halves and halves and so on, as you would see that here. Okay. So this exponent just represents the number of halves that we divided down to. So if we write it out, we would say that n is going to be equal to 2 to the power of k. So if we need to solve for k, k is going to be logarithm 2 of n. Okay. So in the binary search, in the worst case scenario, you would have T of n is going to be log 2 of n. Or, right, if you want to use natural log, you can say natural log of n divided by natural log of 2. Okay. Whichever is easier for you to use in your calculator, that's totally fine with me. And log 2 of n is the power in which the number of 2 is raised to obtain the value of n. So I included this table here so you can see, right? On 1,000 element, we compare the algorithm, and you would see that how many comparison it would take. And so you can see which one you would go with. Definitely programming wise, right? This is the easiest one. We just implement a loop. Okay. This one requires a little bit more. And then this one requires a little bit more. So if you understand the mathematical concept in how these things, right, the mechanism for the searches, it's simply putting that into the language, into the programming language. So here, it asks you for number 6. When searching an array that contains 8,400 elements, how many comparison must be performed in a binary search to find the result? So we know that worst case scenario, we have log 2 of n, right, for binary, or it can be written as natural log of n divided by natural log of 2. So you take your calculator, you go to scientific mode, okay? Natural log is here and log is here. So whichever you want to use, that's fine, right? So I can say natural log of 2, oops, sorry, 2, and then take natural log of that, then divide it by, okay? Wait, I did that wrong. 8,400 natural log is this, divided by, right? We can put it in parentheses if we want to natural log, which gives you roughly 13 comparisons. So I rounded off a little bit there. Okay. So let's say that if it takes half of a second to do one comparison, right? How long does that take? Okay, very fast, right? There you go. And it's faster than half of a second, by the way. Okay, so now if we use the same number of inputs and we put that into chunk search, we wanted to see how many comparison. So for B, you would do, so your T of n is going to be 2 times square root of n. So first, we need to establish our chunks. So take 8,400 and take a square root of that, you would get about 91. And then we would take 2 times 91, which gives us 182 comparison. And if we take half of a second to do one comparison, this is definitely slower than 6A. Okay. Any question? So for quiz and exam, make sure that we know how to calculate, right, your T of n for chunk, binary, and linear. In the case of linear with 8400, worst case scenario, unordered linear search, it goes through everything. So 8400 comparison, because that's the number of input. That's the slowest out of the three. Any question on 6? All right, so let's try with 7, since we already know how to do the calculation. When searching an array that contains 9,750 elements, how many comparisons must be performed in the binary search? So again, this is your n, is the number of elements. So you would take natural log of 9750 divided by natural log of 2. And you are going to have 13 comparisons. So if you look at 6 and 7, right, definitely different number of elements, 8,400 to 9,750, like what, 1,000 plus elements in difference, but still when binary, we have about 13 comparisons. For the jump or chunk search, we would take the n, which is 9,750, and we take a square root of that. So our chunk is going to be 99, about approximate. And then you would take 2 times that, which gives you the result. And I didn't calculate that out. You can punch that into your calculator. That's easy. And then, of course, your linear search, your T of n is n, which is 9,750. Question? So just like number 6, we're just using different number of elements. And you can see there, and you can compare the 3 algorithm. All right. Any question on search? Okay, so that wraps up the search part. We're going to talk about sort next. And I'm sure some of you learned sort, like bubble sort and things like that in C++ courses. But let's talk about how these are different, and we're going to look at the mechanism in the sort so we are clear. Okay, so to start, we're going to talk about insertion sort. If you ever play cards, you do this, right? When you dealt hand of cards, you would organize your cards. So let's say that I get a 2, a king, and a queen, and then a 4, right? I would take the 4 from the back, and then I would insert it between the 2 and the king, because 4 is less than the others. Okay. So here it says that it's a method of sorting cards. It's a way that we can insert a value in a certain position to really rearrange it so that way it becomes ordered. Now, if we look at the example here, you have 34 is in the first element, and then subsequently you have these values. So you would take the 16, right? And you need to move it to in front of 34 because it's less, right? So in programming, we cannot just swap it, okay? We cannot just move it in front of it. You have to take this and put it into a memory location like a temp variable. And then move 34 back one index. It's gonna be I plus 1. Then you're gonna take that value and then put it in front of 34 by taking from the temp and then put it there, okay? So that's what I call a triangular move. You take that, put it into temp, put it into the first index, take what is in the first index, move it over first, or, before that. Okay, there's no magic. You can't just put it in the air, okay? You have to put it in a temp location. So insertion sort is a way that we can take that value and insert it into a certain position, but before that, we have to move it into a temp location. You'll see that this week. So what we would see is we push the 34 value back, we insert, we make that space available, we put 16 there, right? And then we would take that 34 and compare. So eventually what you would see is that it's gonna then rearrange everything from low to high, because even if you put the 16 in the front for the next round, you're gonna take the 12 and then insert it in front of the 16 again, take the 11, insert it in front of the 12 again. And then when it gets to 54, since it's higher, right, we would just keep it in the last element. Then we would move the 10 to the front, 65 after the 54, because then we would compare it to the maximum value. So in this sense, we have to see the minimum and the maximum value on how we want to use those to compare. Okay, to check again so that way we can move our values to the specific index. Okay, so in the phase 1 of the algorithm, the first array element is examined. In phase 2 of this algorithm, the second element must be examined and compared to the first, which must therefore be examined again. So in the kth phase of the insertion, the element must be examined, and in the worst case, it may be compared to each of the previous element, which is k minus 1. So can you implement recursion with this? You can, right? Assuming that you don't hit a ceiling with insertion. So meaning that if your input is meeting the limit, if you have a very large number of input or a very large container, you will hit a limit with recursion if you want to implement recursion. Okay, so now let's do the assignment. And I want to use the table to kind of, walk you through on how it would be sorted, but you don't have to recopy the table. You can just write down the step. So in the first phase, what's happened? In the second phase, what's happened? That's what I'm interested in as the answer. So sort is going to begin at the second element comparing to the first element. So it's going to do 6 with 87. If the second element is less than the first, in this case it is, then the second element is placed before the first. but it needs to move to the 10th, then move there, right, in programming. If it is higher than the first, it would stay in its place. So since 87 is higher than 6, 6 is placed before 87. Okay, so that's after the first iteration, we would see the 6 before 87. Then now what we're going to do is we are going to check 87 with the next one, which is 14. So then 14 also going to check with the 6 because we are interested in taking this 14 and insert it into either before or after 6. So if 14 is greater than 6, it's going to put it behind 6. So 14 is compared to the first element. If it's less than the first, it's then going to compare to the second element, which is compared to the previous iteration. Then it's placing the before the first. If it is higher than the first and less than the second, it's placed after the first and before the second. And if it is higher than the second, it is placed after the second. So it's using the second value as a max and the first value as a minimum, right? So if it's less than 6, it's going to put it before. If it's less than 87, it's going to put it before the 87. And all that is we can use criteria through conditional statement to implement this. So after the second iteration, you would see 6, 14, and 7, 87. And then it can continue after that. Then it's going to take 60, check it with 6, and check it with 87. Okay. I'll leave it there for a little bit. Any question? So in this exercise, we simply just want to understand how it moves the number to rearrange it. And this is insertion sort. It inserts the number into the position for the order. Now, when you're looking at the specific comparison, right, and that is really, it needs to execute that. So we can also look at how we would measure that to really see how fast or slow the algorithm is. Any question on 8? So you can also follow the example in the book and in the notes. So in the worst case scenario, you would see that it would be n-2 plus n-1 plus n. And it's going to be the total number of elements that's going to be examined. In the next sort, we are going to look at selection sort. So it's going to select the smallest one and it's going to swap it. Okay. And the way that it's swap it, it's going to move it to the front. So when you look at this, this is the same example, the same container as the last. So this is the array that you're given: 34, 16, 12, 11, 54, 10, 65, and 37. It's going to look at the minimum value, which is going to be 10. And it's going to take that 10 and put it into the front. And since that's the lowest, it's going to be looking at the next lowest, which is 11, and putting it next to 10. So that will be a k plus 1, right? And then so on. So it's going to go with the smallest and the next smallest and the next smallest after that, and so on until it gets to the end. So we would then have an ascending container, an ascending sort container at the end. And need to take a note that this is the same sum as the given analysis in the insertion sort. It's only backwards. Okay. So in the swap, you're still going to have to move it into a temp variable or a temporary location, and then be able to move the other one over and then move it into its place. And the lowest is going to be index 0. So now for the next part, right? For number 9, given the data, provide the explanation on how the selection sort can be used with the given data. So we have 41, 7, 12, 83, 3, 40, 16, 2, 71, and 6. So in the first round, it's gonna look at the lowest value, which is 2, and it's gonna swap it with number 41. And I highlighted that in yellow. Then in the next iteration, it's gonna take a look at the next smallest value, which is gonna be which one? 3, right? 3, and it's gonna swap that with 7, even though 7 might be the next lowest value, right? But it's still gonna move. So you see here, 3 is take the position of 7, and 7 move into the 3. Okay. Then next, it's gonna be 6, and 6, since it's in the last index here, right? It's gonna swap with 12, and so on, until it rearrange everything completely from low to high. And this is selection sort. So the difference between this one and the insertion, right, is that we, in the insertion, it starts with the first 2. Here we do start with the first index, but we are also looking at the smallest value and swap it with the first index, put it into the first index. And then we continue to swap until we get our sorted container. Any question with selection sort? And again, you don't have to add all the details in the table, as long as you can tell me each phase on which numbers is swapping and how it's rearranging. I'm fine with that for number 9 and 8 and 10. All right. No question on selection sort. So we are going to do a few programs this week on search and sort. And I might not hit all the algorithm, but I want you to be exposed to the algorithm that you can implement. Okay. So as the book highlights some of these, we want to make sure that we apply it. You can see that in C++. Okay, so for 10, we're given the data. Okay. This is our container and it's containing these values. We're going to look at the merge sort. So if you go back to your notes, it talks about merge. And this is known as the divide and conquer algorithm. Similar to what you've seen in binary search, this is a way that we sort by dividing. Okay. So when you start with an unsorted list, you want to make sure that you check, right? So if n is equal to 1, it's gonna return, it's gonna exit. But if you have, let's say, more than one element, let's say you have 2,000 elements, it's gonna take that container and then divide it into half. So I have 2,000 divided into half, I would have 1,000 and 1,000. And then I keep dividing again, right, into the smaller subsets. Then it's gonna, as it's after it divides it up, then it's gonna merge them. Okay, it's gonna combine the smaller subsets first, and as it does that, it's gonna reorder. So merges take two sorted lists, combine them repeatedly by comparing the lowest elements and sending the smaller one off to be the next element in the combined list. So it breaks down to all the smaller lists. And as it goes down, it's going to compare the smallest value. It's going to put it into the first index and the next one after that. And it would merge it back as it compares. So this is called a merge sort. And in the example here, you see that this is an unordered container. It breaks it into halves. So it divides this container into half and then into half again, and then into half again and halves until it gets down to the single element. And when it merges it, it's going to compare which one is smaller. Smaller one takes the position before. So that will be I minus 1. Okay. So we would merge these back. 3 is less than 4, right? 4, let's put 5, and so on. So when we compare these three, you would see that insertion, selection, merge, and there's another one called quick sort, which is about the same as the, well, this one implemented like, it's almost about the same as your merge sort. Okay. So you would see that what would be the worst case scenario. So in insertion and selection, you get about the same, n squared. In merge, it's n log of n. Okay. All right, so now let's work on number 10. So you're given this container. Let me move this to the next page because for some reason it cuts it off. I have like an orphan paragraph on the next one. All right. Now let's move this up. So what we do is we are going to take this container, and I highlighted how it's going to take that, the first half here and the second half. Okay, so it's going to break the list into 2 equal pieces and apply the merge sort in each piece. So we would start with this container, and then it's going to break that into two subsets, 35, 19, 66, first set. The second set is going to be 4, 10, 28, and 6. So that's the second half here. Okay. Then it's going to take those halves and it's going to divide them again into more halves. So then it's going to be 30 and 5, 19 and 66, 4, 10, and 28, 6. Then it's going to divide again into additional halves. So we would take this and cut it again. Okay. So now what we would do is then we would merge them back, right? 5 is the lowest, so it's putting that in the front. 19, 30, 66. Then on this, the second one, it's going to do 4, 6, 10, and 28. So it's going to merge and order combine 4 sublists to 2 sublists. Then it's going to merge them back for to the 2 sublists to 1 sublist. So I tried to illustrate this by typing out the numbers so you can see. So it breaks it down into halves until it gets to the very small halves. Then when it merged them back, it rearranged the order based on the smallest value. So there you have it. You would have a merge, sort, divide and conquer. So it divides into halves and then merge them back in order. Any question? Let me zoom back into 100 so you can see everything there. And again, make sure that we know the difference between or amongst the sort algorithms. That's important. You will see these questions are similar to these on the exam and your quiz. Okay. So this is not a very difficult chapter. It's fairly easy. It goes over just search and sort. And compared to some of the, the prior chapter or even the later chapter, this one is pretty easy. As long as you know the difference, right? The algorithm and that for search and sort, you'll be fine. Okay. And then I had typed out some table there, but you don't need to look at the table. Any questions on these? No questions? All
Will we
right.
have to know any other searching algorithms or anything? Or
Not
shortcuts?
for this class, no. But yes, that's a good question because so no, not for this class, but in your field, yes, you can implement your own algorithm but there are many people that have created search and sort algorithm that, that's used in the field. If you're using a library, Okay, this is my recommendation. If you're using a library for search and sort functions or methods, make sure that you read what kind of search or sort is it using. It doesn't necessarily mean that it's the fastest if you're using a library. It's just library is convenient. You can import into the import the library and then use what's already pre-written. And that's what we should be doing, is to use existing tools. But if your objective is to make sure that it's really well performed, then you need to investigate what kind of search and sort that is. And these are some of the common main ones that you see, but yes, there are others. And so you just need to take a look at how they solve the search and sort, how it's implemented, into the program. Okay. So for our class, only the ones that are discussed here. Any other questions? Okay, no other questions? All right, that's all I have for you today. We finished a little early today. Type your name into the chat if you are already. Let me stop recording.